Great. Now let us repeat something that we discussed briefly, but there are other aspects that we are going to bring up today. What happens when you have a matrix that is Hermitian? And now I think we understand this equation, we understand what is the meaning of I, right. What is the definition of Hermitian matrix? A equal to A dagger, or A equal to A transpose, or A equal to, or A into A dagger equal to A equal to A dagger. And what happens when A inverse equal to A dagger? A inverse equal to A dagger. It is unitary. There is no reason to be scared. It is unitary. Fine. So now what we have said is that you take the adjoint of the two sides, then you have the dagger of AXI is equal to the dagger of lambda I xi, very simple. I just put in a pair of brackets on both sides and put in a dagger, okay. And then the thing is, you should work this out yourself, that the dagger of AB is equal to B dagger into A dagger, not very difficult to work out. I leave that as a homework problem. And do not forget that now I think there is no confusion, we understand that lambda I is a scalar quantity, right. So if that is the case, will you agree with me that the first equation here, rather the second equation, goes on to become xi dagger A is equal to lambda I star xi dagger, right. And people like him are going to need lambda I star, right, because he got an eigenvalue that is imaginary, complex, okay. But then his neighbor is not going to worry about dagger, about star rather, because the eigenvalue he got is a real eigenvalue, okay. But of course we know that star is going to go at the end. Now what you do now is that you right multiply by xi, okay. Multiplying by xi, this is what you get, xi dagger AXI is equal to lambda I star xi dagger xi. Why do I right multiply by xi? Why not left multiply? So if I left multiply, then I end up with not much. If I right multiply, the good thing is that AXI is there and we know what AXI is. AXI is lambda I xi, okay. So it can get simplified a little bit and I can write xi dagger lambda I xi, and I can rearrange it to write lambda I xi dagger xi, lambda I is a scalar. So lambda I xi dagger xi is equal to lambda I star xi dagger xi, right. What is the next step? Make one of the sides 0, right. So you have lambda I minus lambda I star equal to lambda I minus lambda I star multiplied by xi dagger xi equal to 0, okay. Now what is xi? Okay, so it might sound like a foolish question at this point, but I do not want us to lose track. What is xi? It is the ith eigenvector, right. So now you see, if I take the adjoint of an eigenvector and then multiply the original eigenvector by it, what should I get? You can work it out yourself. What I am saying is, you have x1, x2, x3, so on and so forth, and since I is common, I am not even writing the second I. If you want to write, you can, there is no issue. So I have what, a column vector, right, x1, x2, x3, x4, etc., right. If I take this xi dagger and multiply it by xi, what should I get? Summation of square. What kind of square? Square, okay, you said square terms. So is it summation of square terms exactly, or you want to modify that a little bit? Xi star x1 star x1 plus x2 star x2 plus x3 star x and so on and so forth, right. What should that be equal to? that should be equal to 1, right? It has to be normalized, and it would better not be normalized. If you want to normalize it to a value other than 1, I have no issue, right? That happens many times, but you better not normalize it to 0. You that is not a good idea, right? Let us not do that. So, the thing is, whatever it is definitely not 0, right? So, if it is not 0, what does this mean? It means that lambda I minus lambda I star has to be equal to 0, or in other words, lambda I equal to lambda I star, right? Oh man, I have become so predictable. In other words, he stole my line. The eigenvalues are real. Okay. So, this is something that we encounter everywhere, right? We use even mechanically that when you have a Hermitian operator, then you are going to get real eigenvalues, and this is how it comes from matrix algebra. Now, but we are not done with Hermitian matrices yet, not today. Now, let us have some more fun. We have said that these x values, they are normalized, right? Now, are the eigenvectors orthogonal? Are these eigenvectors orthogonal or not? Let us see. Of course, the default answer, keeping eyes closed, is yes. If you study physical chemistry to a certain extent, sometimes you can even guess what is going on. There was this not physical chemist with whom we were discussing some problems in some context once, and then there was this thermodynamics problem where you have to find delta H, and this gentleman said, if I were to write the answer, I would have just written 0. Oh, physical chemistry में सब कुछ 0 ही हो जाता है, and as luck would have it, the answer was actually 0. So, it is like that, yeah, they are going to be orthogonal, but let us see how it comes. Okay. So, you start with 2. If I want to talk about orthogonality, then I cannot work with only one, right? I have to take 2 vectors. So, let us say k and L, xk and xl, axk equal to lambda k xk and axl equal to lambda l xl, right? Take these 2 and proceed more or less in the same manner as the previous derivation, okay? Well, animation gone wrong, what to do, but just take the first one and take adjoint. This is what you get. Do you agree that this is what you get? Xk dagger A equal to lambda k xk dagger. I have not written star, why not? Because I have the benefit of hindsight. We just proved that Hermitian matrices are going to have real eigenvalues. So, I have saved some ink by not writing star. Okay. Now, what do I do? What did I do in the previous derivation? I right multiply, right. So, this time also we want to right multiply, but not by xk but by xl, that is right. So, I get xk dagger axl equal to lambda k xk dagger xl. Right. So, once again you know very well what is axl. Maybe I should have chosen a different subscript. XL sounds funny. Alright, axl equal to lambda l xl, isn't it? So, take that and plug it in, you get lambda l xk dagger xl equal to lambda k xk dagger xl. Yeah. So, transpose, you get xl minus lambda l minus lambda k, I am now obsessed with xl, lambda l minus lambda k multiplied by xk dagger and our favorite xl equal to 0. Alright. So, what will be the next step? Xk dagger into xl equal to 0. When? When lambda l and lambda k are not the same, right. So, if I write xk dagger xl equal to 0, will you allow me to write that the eigenvectors are mutually orthogonal, right. So, now we have proved that the eigenvectors are mutually orthogonal also. and that is why they are so useful in application in things like wave functions, quantum chemistry. Alright, so far so good. If it is equal to lambda k, it can be, but then they are not going to be mutually orthogonal, it is going to be the same vector actually. Okay. Now this is something that I leave it to you, it is not very difficult. You have to, I want you to figure out, convince yourself, Zy is not happy at all, but then you work it out, you will convince yourself that X, that big X matrix is unitary. What is X matrix? Yeah, so this eigenvector 1, eigenvector 2, eigenvector 3, so on and so forth, that matrix is unitary. How will you do it? You take the adjoint and then multiply the adjoint with the original matrix, but when you do that you have to keep in mind something. What do you have to keep in mind? This orthonormality condition. Okay, you keep that in mind and you see what should the product be if it is unitary. Product of the adjoint and the matrix itself, what should it be if it is unitary? Should be unit matrix, right? What is the definition of unitary matrix? That A inverse is A dagger, right? So this is what you have to show. X dagger X equal to E. I leave it to you to do that, it is not very difficult, just do not forget the orthonormality, then you got a problem. Okay. Now let us maybe rush through this, we have done this once already. So if Q inverse A Q equal to B, then det A equal to det B, this is what we want to prove. You start with this, det xy equal to det x det y, right. How do we do it? We do it using an example of 2×2 matrices. And this is what we had discussed earlier also. Xy is this. So what is det xy? I spare you the trouble and write it down myself. But then you can perhaps figure out that these two determinants are going to be 0. So it is not very difficult to see that it is, this gives you det x into det y. Okay. Now with that we need to see if this is correct or not. If Q inverse A Q equal to B, then det A equal to det B. I am doing this again because there was a little bit of confusion last day, and then we are going to use this in what we are going to say today also. Almost maybe 10-15 minutes more, almost done, do not be impatient. Okay. You agree with this? The det B equal to det Q inverse det A Q. You have started with B equal to Q inverse A Q, right. So I can write it like this, expand det A Q and write det Q inverse det A det Q, and determinants are just numbers, so it does not matter in which order you write. So I can write det Q inverse det Q det A, and det Q inverse det Q, as we have seen earlier, det xy equal to det x det y. So this becomes det Q inverse Q. What is Q inverse Q? Unit matrix. So it becomes det E. And what is det E? 1. So this becomes det A. Then it is proved. If B and A are conjugate to each other, you have not forgotten the term conjugate, right? Similarity transforms also go by the name conjugate. If A and B are conjugate to each other, then the determinants are the same, and this is only the first of a list of things that are same for conjugates. The determinants are the same. Next, what we want to show is that conjugates have the same eigenvalue. If A and B are conjugate to each other, then they should have the same eigenvalue. Start with this, B equal to Q inverse A Q, and then let us write minus lambda E on both sides. So now from there, will you allow me to write Q inverse A minus lambda E Q? Can I do that? Lambda is a scalar and E is unit matrix, that is why I can do it, right. So then you get det B minus lambda E equal to det Q inverse A minus lambda E Q, which gives you det Q inverse det A minus lambda E det Q. Then again you can write Q inverse and Q together, and finally you are going to get determinant of A minus lambda E, right. So since they are identical equations, you get identical roots. If you get identical roots, then you have the same set of eigenvalues. Right. Next, second last today is if A and B are conjugate to each other, then they have the same traces. And this is of utmost importance in our discussion in chemistry, in symmetry, because if A and B are conjugate to each other, then they belong to the same class, right. What is the definition of a class? It is a set of elements that are conjugate of each other, that are conjugate to each other. So what we are going to show here is that they have the same traces. So trace B is sum over I BII, okay, and pardon my mixing capital letters and small letters here, somehow I felt that I could not write small q inverse, that just did not sound right. So but I think you understand what I mean. So instead of BII I can write Q inverse A Q, and in order to get II, this is how the subscripts have to be IK, KJ, JI. That is something that comes from basic matrix algebra, I think all of you know. So I am going to get Q inverse IK. What is the meaning of Q inverse IK? Which element? Ith row kth column or ith column kth row? Ith row kth column. Latitude longitude is important. If you mix up latitude and longitude, then instead of coming to Bombay you might reach, I do not know. So the ith row kth column element of which matrix? Q inverse, and similarly you know what is AKJ and what is QJI, right. So now I separate A because Q is there, Q inverse is there, I can easily get rid of them. So it will be sum over J, sum over K, AKJ, sum over I, QJI, Q inverse IK, right. Will you agree with this now? Can I combine this as Q inverse JK? I am multiplying, right? I am multiplying Q with Q inverse. Not only that, I am multiplying this QJI with Q inverse IK. So what I get is that once again it is as if this second subscript of the first and the first subscript of the second cancel. They do not actually cancel, but it is easy to remember that way, okay. So when you multiply them together, what you can write is, you can write Q inverse and the subscripts are going to be JK, alright. And what is Q inverse? E, spoil sport again. Q inverse is E. So now in E, what happens when J equal to K, that element is 1, and when J is not equal to K, the element is 0. So I can write our favorite Kronecker delta, delta JK, right. AKJ delta JK sum over K sum over J, right. What do I get then? Once again multiplying, so it is as if JJ's cancel off and you are left with KK sum over K AKK. What is that? The trace, right, or the name that we have used earlier when talking about those transformation matrices is character. Now we have talked about reducible representation, we have talked about irreducible representation and so on and so forth. So now does this depend on whether the matrices we are working with belong to a reducible or an irreducible representation? No, right. Who has talked about reducible or irreducible representation here? Nothing. I am only talking about some matrix, right. I am only talking about two matrices A and B. The only condition is that A and B are conjugate to each other. So, no matter whether the representation is reducible or irreducible, it does not matter. The traces of matrices that belong to the same class are going to be the same, alright, and this is something that we will use extensively when we discuss character tables. Okay. Last topic of discussion, and this is also something that keeps coming back to haunt us in many places, it is very important. Sounds a little funny. A unitary transformation leaves a unitary matrix unitary. It is almost like poetry. Too many unitaries, right. Unitary transformation leaves a unitary matrix unitary. Let us see. Let us say then, let us start with this, that X is U inverse A U, where A and U are unitary. Alright, we start from here. There is a meaning of a unitary transformation. What is the meaning of unitary transformation? Yeah, that? No, but what is a unitary transformation? When I say unitary transformation, what does it mean? So, the matrix that is being used to do the transformation, that is U, right, U inverse U, that matrix is unitary, that is all that it means. Now, what we are saying is that if A is also unitary, then X should be unitary as well. Too many unitary we said too many times, please do not get confused. Unitary transformation has got to do with the U's, okay. When I say unit, suppose it instead of A it was some matrix P which is not unitary, even then it would have been a unitary transformation. Is that, I mean, am I a little clearer now what I am trying to say? The U's have to be this U and this U. When I say U's, once again it is confusing. This U and this U, well same U actually, U and U inverse, that is the unitary matrix, U for unitary, okay. That is the meaning of unitary transformation, and when you perform a unitary transformation on a unitary matrix A, then our contention is that the matrix X that you get is also unitary. That is what we are going to learn, alright. A unitary transformation leaves a unitary matrix unitary. Let us see. Will you agree with me that X inverse is U inverse A inverse U? How? Start left multiplying. X equal to U inverse A U, isn't it? So, if I want to keep on left multiplying, what should I get? If I want the inverse of X, then I should left multiply by the inverse of the first element first. So, that gives you U. Next will come A inverse, and finally you will get U inverse. So, you get U inverse A inverse U. Are you okay with this? Sometimes the order becomes confusing. Are you okay with U inverse A inverse U? Are we convinced that it is X inverse? Sure? Now, so if you are convinced, will you allow me to write it as inverse of AU multiplied by U, right? Inverse of AU multiplied by U. In that case, next step is easy. Then X is AU multiplied by U inverse. Multiply AU first, A and U together, then multiplied by U inverse. So, what is the adjoint of X? X dagger. It will be dagger of AU multiplied by dagger of U inverse. Right? So, that is going to be U dagger, A dagger, dagger of AU, AU inside bracket is U dagger, A dagger. I think you were asked to work that out or something. U dagger, A dagger multiplied by U inverse dagger, and we are done. We are done. U dagger, A dagger and dagger of your A inverse. Are we okay with this so far? If you are okay with this, then we are done, because U dagger is U inverse. Do not forget that U for unitary, right. A dagger is A inverse. And now U minus dagger is most interesting, because U minus dagger would means inverse of U inverse. U inverse of U inverse is U. It is just that if I want to touch my nose and I kind of go around my head, that is that kind of thing. So, that is U, right. And what is U inverse A inverse U? Will you not agree with me if I say it is X inverse, right, because we have started with X equal to U inverse A U. So, what do we get? We get X dagger equal to X inverse. Is that not the condition for X to be unitary, right. So, we have proved this somewhat funny sounding theorem, that a unitary transformation leaves a unitary matrix unitary. Okay. So, we stop here today, because yeah,
the third step where
yeah,
X is equal to AU into U inverse,
hmm,
from the previous step the order should be reversed. Because
Why?
Inverse is AU inverse is U. Yeah, that is.
I was also thinking that, but I do not think so. Okay, you work it out. Let me also work it out myself. I do not think it is a problem. And then what we do is, now from this we go on to something that is perhaps a little more abstract, perhaps not. We start talking about function spaces. Have you function space? Have you studied this in some course or the other? Huh? In what? Okay, yeah. This function space, I mean, it sounds scary, but there is no reason to be scared about. I should be scared because while teaching first year BTech course, once I had said, let us say I have n dimensional space and this smart Alex stands up and says, no, you cannot talk about n dimensional space. I say, why? And I say, space is 17 dimensional. Huh? What are you talking about? Yes, space is 17 dimensional. We have been taught in physics, they had used to study relativity at that time. I do not exactly know this 17 dimensional thing, but present Dean Essay is the one who had taught them that. So, I do not know what the 17 dimensions are. But anyway, the thing is this, when we talk about space, we generally think of 3 dimensions, isn't it, x, y and z. But then suppose I have something that is dependent on more parameters. So, basically I am talking about equation like y equal to x1, a1 x1 plus a2 x2 plus a3 x3 and so on and so forth. Can we not have equations like that? We have already had equations like that, we have encountered today also, right. So, that is what takes us to n dimensional space, right. So, space is not space, it is just an analog of space that we are talking about. Now, think of say position vectors, you know position vectors, right. So, if I am the origin, this is a point, this is a position vector, right. Well, everybody is origin with respect to himself or herself. This is another position vector, this is another position vector. How many position vectors are there? Infinite. So, these position vectors constitute a function space. But then the point is this, all these position vectors can be represented as something into x plus something into y plus something into z, right. So, those are the kind of normal modes, orthogonal modes of this function space that is defined by position vectors. Okay. So, that is what we will start talking about, and then we need this concept to develop great orthogonality theorem, and we will talk about something called OR, transformation operators. So, that will require one class at least, and then we move on to reducible and irreducible representations, that will be next week. Week after that we finally get to our orthogonality theorem the great, and after that it is very simple. It is just using orthogonality theorem to derive the character tables, using character tables to figure out lots of stuff about whatever molecule that you want to. Okay. That is how this course is going to go from here.